So I figure we can pick up with more linear logic today, and the first thing I wanted to do was before I get started I first wanted to find out if anyone had any questions from yesterday's lecture. Like, is there anything weird or just anything you're just curious about? Oh, fantastic. Everyone is like completely on board with this. I find this a little difficult to believe, but I'm willing to accept it. Okay, so, yes?
I was actually maybe hoping, I guess, more intuition for the use of F and G. I mean, I get why they're there, and I'm trying to read the paper, but you're right. They mostly explained it in the category theory sense. So
yeah.
Maybe the intuition would be great.
Okay, that's a good question. So let's see, what's the best way of explaining this? So, there's actually several possible explanations, and I'm not quite sure which one, like at what level you're confused. So, you want to know, like, what makes it the right thing, or like?
Yeah, I guess how the inspiration kind of came to be.
Okay. Well, okay. Yeah, I can talk about that. It's a little bit of a digression, but it's still interesting. So let me blank the screen, and then I'll talk about that. Okay. So originally, when linear logic was invented, Girard had the idea that linear logic could be understood as a refinement of ordinary intuitionistic logic. He said, in intuitionistic logic, you are free to use a hypothesis as often as you like. It might be 0 times, it might be 1 times, it might be many times. And linear logic can be seen as a refinement in that you can make distinctions about proofs that you couldn't before, because you can only use a variable exactly once, sort of your proofs can count now. So a tensor A is different from A. So in linear logic, a tensor A is most definitely not the same thing as A. Whereas in intuitionistic logic, if you have A and A, that's exactly equivalent to having A. Like, this is one of the basic properties of having a conjunction. And so, okay, it's always nice to say, okay, this logic can make distinctions, or this language can make distinctions that the old one couldn't. But if you can't say all of the things the old language could say, you've also lost expressiveness. And so Girard's idea was, he said, okay, we have these basic linear connectives like tensor and lollipop and the unit, but how do we get back to intuitionistic logic? And he said his idea was that you could introduce a new connective to linear logic. So you would start out with just the pure linear calculus. And this would be like a very impoverished language, and consequently an extremely well-behaved language. And you could regain the ability to count, to use hypotheses multiple times by adding a new type operator, which he called bang. And this is sometimes also called the exponential modality. And what this means is all of the connectives except for bang are connectives that can be used exactly 1 time. And bang A is something that you can use as many times as you like. And so the idea was that then once you have a bang of A, you could use this to do a type encoding of intuitionistic propositions into linear logic. So what you would do is you would just sort of hit everything with bangs in all the appropriate places. So you could say, well, the one I can encode as like bang 1. A tensor B will be bang of the translation of A, tensor bang the translation of B, and that part should all make sense. And then the bit where he got clever was when you have A implies B. What you would do, actually, let me be consistent with my notation from yesterday. X times Y, X arrow Y, and make those X's. And then his idea was, you would say, well, an intuitionistic function is something that can use its argument as many times as it likes. So what we'll do is we'll translate the argument, hit it with a bang, and then send it to the translation. And then the whole thing you can use as often as you like. And so in this way, he was able to code up the ability to use a hypothesis many different times. And one issue, though, was that the semantics of the exponential were quite complicated. And this was the subject of rather a lot of work over a period of about 10 years. And the sort of at a semantic level, what Nick Benton and Phil Wadler did was they observed, actually many people had observed, that this bang is a comonad. So if you've done functional programming in Haskell, you're probably very familiar with monads. And you know, the property of a monad is you have a return operation which says something like, if you give me an A, I will give you a T of A. And it'll also have a join which says something like, oh, if you have a T of A, then I can squash it down into a T of A. And a comonad is going to have these operations, but turned around. So we might say, okay, you have a function x, which if you give me a bang of A, will give me an A, and we'll have a duplication operation, let's just go, which says, if you have bang A, you can send it to bang bang A. And so it's exactly like a monad, except all the arrows go in the other direction. And so it's a comonad rather than a monad. And the semantics of this comonad were quite tricky to figure out. And the discovery that Nick Benton and Phil Wadler made was that all the mathematical semantics got much simpler when you thought about when you thought about it in terms of this F and G. So categorically, like every monad and every comonad arise from an adjunction. And what this adjoint calculus does is it makes that adjunction explicit in the syntax. So that's sort of the semantic reason why this thing exists. The operational reason, like the programming reason of why you want it, maybe I can illustrate by writing a C program for you. So we'll sort of go from the sublime to the ridiculous here. Yes?
Sure. Bang bang there's the main concept or the thing that takes you to bang still applies to?
Sorry, could you repeat?
I don't understand. What is the domain and codomain of bang exactly?
So in the original presentation of linear logic, there's only one category of types. And if A is a linear type, then bang A is also a linear type.
Okay, so you can keep applying.
Yeah. Whereas in the adjoint presentation, there's like two universes of types. And so it turns out that bang of A in original linear logic can be encoded as F of G of A. And it's sort of a good exercise to see if you can figure out from that encoding how to implement these two functions. So with this encoding, try to work out how you can get from bang A to A, and also try to figure out how you can do a so now, like the reason that it's nice to be able to talk about both intuitionistic and linear things is that when you're programming, there are often values that require you to sort of think in like a kind of subtle way, where certain operations it's okay to do things linearly, and in other cases you have to think about linearity or in a careful way. And so let's see an example of this. Let me make that a little bigger. Okay, can the people in the back read that? Or should I make it a bit bigger? What? Okay. And does the video pick it up? Okay, great. Okay. And so let's do the usual ceremony for writing a C program. And this isn't going to be like a super fancy C program, because I'm not like really a great C programmer. But there's going to be something that happens in it. And the characteristic thing about C programming is that when you allocate, you can explicitly allocate memory, and you can explicitly deallocate it. So let's allocate some memory. And so what we're doing in this first line is allocating a pointer. So we're calling malloc, and we're going to just get a pointer to a word of memory. And now that we've created this value, there is an obligation that we have to do. So if we want our C program to not leak memory, then we are obliged to deallocate it. And so at some point, we must call free on this. And we must also call free on this exactly once. So we can't forget to free it, because that would lead to a memory leak. And we can't do a double free on it, because that would mean that like hackers on the internet will take control of our computer. So you can see that this malloc free behavior you really need to treat in a linear way. But at the same time, these pointers can be used in certain ways that are not linear. So make that go away. Okay, don't know why. Let me just shut this down. Okay, so let's call printf, for example. So what I'm just going to do is I'm going to print this pointer using the %p format specifier. And what this will do is it'll print the address of the pointer to the screen. Let me stick in a new line. And now that we have used this pointer twice, what we're going to do is we're going to do what we promised what the C program demands of us, and we're going to free the pointer as well. Free p, and then we'll be done. Okay, so now let me see if gcc-o foo of foo.c. Oh, which directory is this in? Oh, this is in my home directory. Okay. Okay, so all successfully compiled. Oh, let me make that bigger as well. Zoom in. Zoom in. Okay, so you can see, let me reset here. Let's compile the function big enough for the recording to pick up. And now we've compiled the foo program. So now we can actually run it and see what happens. Oh, and it says, yes, I'm a pointer being used twice. And it prints this, I guess, 16-digit hex string, because this has a 64-bit address space. and it prints it twice. So what's just happened is, from the point of view of a logician, quite interesting. So going back to the program, this program right here is quite odd in that part of it we're handling in a nonlinear way. Like there's no problem at all with printing the pointer's bit representation twice. But part of it is also we have this linear obligation where we allocate the pointer, and then after we use it for a while, we have to free it exactly once. So you can see that there's a kind of some aspects of a pointer can be treated non-linearly, and some aspects of it can be treated linearly. And so as a result of this, it turns out that it's quite convenient from a programming point of view to have access to both linear and nonlinear reasoning in a sort of first-class way. So that's why I believe that you should, when you build programming languages based on linear logic, it's a good idea to treat the intuitionistic and linear things treat both of them put both of them on a first-class footing. Other people think that if there is an encoding, then maybe you should just use that in order to make the kernel language smaller. And people argue about this, and I think at this point it's probably fair to say we still don't know how to do linear types wrong yet. So we need to build more programming languages. Many of you should build programming languages based on linear types, and with experimentation we can probably eventually figure out the right design principles to turn a logic into a programming language. But be that as it may, we still need to understand sort of the kernel semantics behavior of this kind of feature. And in this lecture, what I'm going to do is I'm going to talk about one way of using linear types to build a programming language. So here we've been working with a stateful programming language, and that's a powerful motivation for using linear types, and that's how I'm going to do it. So in this lecture, I'm going to be showing you a variant of a language that Amal Ahmed, Matthew Flewitt, and Greg Morissette developed, I guess, is it 10 years ago now or more? A little more than 10 years ago, called L3. And if you go and look at the paper, you'll notice that what I'm going to show you today is going to actually look different in detail in a lot of ways from what Amal did. And this is in general like a piece of advice that's sort of good for research. Like reinventing wheels is important. You should read a paper, try to do it in your own style, and then once you've run into the roadblocks and worked your way through them, then you'll come back to the paper, and then the bits that you found difficult or hard to understand will suddenly seem insightful and penetrating. So it's okay to reinvent wheels. That's the way we learn. Okay, so yes. Okay. So Frank has done a lot of stuff with linear logic. So it sort of depends which of Frank Koenig's things you'd like me to contrast with. Let's see. A lot of the work Frank did as of up to about 5 or 6 years ago was done in this style. And part of the reason for that is that Frank has done a lot of work on modal logic. And if you can think of this kind of bang as a form of modal logic. And so a lot of the work that he had done allowed him to design very, very elegant very elegant calculi for linear type systems with an exponential modality. And more recently, he's been working a lot on concurrency theory and how to understand things like session types in terms of linear logic. And what session types are they're basically types for protocols between interacting processes. So if you have two processes, like say a web browser and a client, then you sort of need the client to be receiving when the server is sending and vice versa. And so so for any kind of interaction, there's a protocol saying, you send, I'll listen, and then I'll send and you'll listen, and we'll make decisions based on the data we send to each other. And if the two endpoints are following different protocols, or they think they're at different parts of the protocol than they actually are, then the communication will fail. And so what session types do is they let you type an interaction between two processes. And we actually saw just a little bit of that with the malloc-free example, because you can think of that as a protocol between the malloc library and a program. So the protocol says something like, when I call malloc, the runtime system, the C runtime system will give me a piece of memory, and I'm free to use it. And I promise that I'll call free when it's time to give the memory back to the runtime system, and I'll call it exactly once, not twice, or not 0 times. And furthermore, I will not look at that memory after I free it. So, so that kind of I'm going to use linearity to track a protocol. Leads to a way of thinking about the proof terms of linear logic as processes. And I'm going to talk about viewing the proof terms of linear logic as like functional imperative programs. And so this is an example of like why you shouldn't say Curry-Howard isomorphism. You should say Curry-Howard correspondence. And this is because once you have a logic, you don't have any proof terms there. And you are free to equip a logic with any proof terms you like, based on whatever computational interpretation you can make sense of. And it's entirely possible that for a given logic, there are multiple ways of giving it a computational interpretation. And more than possible, for linear logic, it happens in a lot of different ways. So for linear logic in particular, you can think of linearity as talking about like ownership of memory or resources, or you can think about it as like non-interfering composition of parallel processes, or you can think of it as non-determinism, or you can take the linear and linear types completely literally, and you can say the types are interpreted as vector spaces and terms are really linear transformations between vector spaces. So there's a lot of different ways to build a model of linear logic. Okay, well, I should pontificate a bit more for a moment. So this is not on my main line at all, but it's sort of a good thing to tell you all. So and I think it'll also build on what Amal was saying. So part of the point of having a programming language at all is that gives you a way of writing programs for some underlying machine. And by underlying machine, you might mean something as concrete as like x86 or ARM, or it might mean something like finite state automata or Turing machines or whatever. You have some underlying machine model, and you can think of programs as ways of like choosing certain machines from that class of machine models. And so the principles of writing down programs will let you pick out different machines. And moreover, for a well-designed programming language, you have like a good equational theory as well, which tells you when one program is equal to another program. And in practice, this is important for things like compiler optimization. And the sort of the trick or art to language design is you want a language whose reasoning principles are simple, but which maps down to a machine with, like, you know, a good amount of mechanical sympathy. So like you want it to like align with the machine and with the human. And so let's actually look at that today. So we saw before with that little C program that we were going to have both pointers could be used both nonlinearly and linearly. And let me put it back now that I've sent it up. So the trick here is that here on the first line, we call malloc. And malloc gives us a block of memory. So in this case, this block of memory will probably be 4 bytes long. But let's run this program again. And you can see that starting at address 55FEC3C342010, we get some memory from the runtime system. So like our computer's memory is notionally a gigantic array starting at 0. And then at some point, which is 0x55, what did I write down? FE3 whatever, FE3 whatever, I get ownership of this block of memory. And so the value of type of int star p is actually this number, which tells me this is the address in memory. And this address or pointer, the literal pointer value, is something I'm free to use. It's as often as I like. It's just a number. Numbers we can copy or not use as freely, and it doesn't affect anything. But the important thing is that the ownership of this block of memory must be treated linearly. So I can't free that memory twice. I must free it, or the program has a memory leak. So it's the content, it's the sort of the rights to access memory that have to be treated linearly, but the pointer itself we can treat in a nonlinear way. And so this was the sort of the key idea behind the design of L3. So the idea was that and here I'm going to engage in a small amount of revisionist history. The idea behind L3 is we have these two linear and nonlinear languages, and what we're going to do is we're going to break this int star type into two pieces. So we're going to keep the standard types of intuitionistic logic, and to this we'll add a new type, pointer of x. And you can think of this as saying, this is the type of pointers whose value is x, whatever x is. And then to that, we'll add a type, capability. And what this means is, this is a linear type, and it says, I own the region of memory at address x, and I have stored a value of type x into it. And so the idea is that because pointer is an intuitionistic type, we can use it as often or as we like. And because capabilities are linear, we will be able to enforce the property that we have to treat it linearly. Like we have to allocate, every allocation is matched by a single deallocation. And then for reasons that will become a little bit clearer, later, the next thing we want to do is we want to say, well, once we can perform modifications to the heap, we'll introduce a monadic type to talk about these kinds of computations as well. Yes?
Will capability somehow impose ownership?
Yes, so capability, you could write it in many different ways. So I picked cap because that's what was in the L3 paper, but you could also call it like ownership, or you could call it points to or something like that. So L3 wrote cap. If you've seen separation logic before, then you might write it like x points to a value of type x, or if like you've done a lot of C++ programming and you think in terms of ownership, you could say something like the address x owns value of type x, and so on. So like it's the intuition of ownership is the important thing. The notation isn't so important. But you're exactly right that it is the intuition behind this linear type system is that you do own a piece of memory. Okay, and so once you have this, you are now free to we can now say what it means to do things with pointers and capabilities. So let's. What I'm going to do is I'm going to just sort of write down some types for some of these constants. So what we'll do is we'll say, well, once you have a pointer, then there's sort of like 4 things that you can do to it. You can allocate a pointer, you can read from it, you can write to it, and you can free it. And so we can introduce an operation for corresponding to each of those 4 actions. So we can say, I want to have new, and what this is that it's a computation that when I call it, will say, okay, well, there's some pointer. And you get the pointer value, and in addition, I will give you the right to that piece of memory. And what this is doing is it's saying, this is a command that when executed will give you a pointer and the right to access the region of memory that this pointer points to. We'll do some examples in a minute. Then we can also do, let's see, free, which let me back up a moment and let me go through this type in a little bit more detail. So here, this whole thing, this whole T thing, is a computation living in the linear world, and what it's returning is a pointer, which is intuitionistic, and so we stick it in an F, and we pair it together with the right to access that piece of memory. And likewise with free, what we'll want to do is we'll want to say, to call free, what you need to do is you need to give free an address, and then you'll also tell free, additionally, give me the right to access that location, and what I will do is I will take it off your hands. So if you give free a pointer and the capability to access that piece of memory, then it'll perform a computation that gives you nothing. So it's consumed the capability in just the same way that new has created a capability. So if you like, you can think of new as I'm taking something from the free list, and free will put it back onto the free list. Yes? Do you have a question? Okay. And next, we'll also have a read operation. And what read is it's the pointer dereference operation, and it will say, if you give me a pointer and a capability then what I will do is I will give you the contents of that pointer. And I'll give you the capability back. You haven't lost it. So, you know, we give read a pointer and a capability, and it'll give us the content of the pointer. And we can also do a write. So, you know, we can do write. And again, in order to do a write to a pointer, we need the actual address to use. And we need the capability to access that location. And we need a value. And once we perform the write, we'll get back an updated capability. And one thing that's worth noting is that when you treat capabilities explicitly and linearly, you gain an ability that you don't have in a language like Java or ML. So here, what write is saying is, give me a pointer pointing to x, and then give me a y, which could be of a completely different type. And then when I perform the update, the type of that pointer will change. This is called strong update, and you know, when you're implementing systems, it's sometimes a useful thing to be able to do. Like you start in an uninitialized. Yes. Oh, it should be f of y. Yes. Was that your question? Oh, okay.
Is it number or is it type?
Oh, it's a type. It's the unit type. Yeah. Yeah. So what this is saying is, like we didn't give new a value to initialize the pointer with, so we just picked unit and said there's some unobservable junk there. And so what we'll do if you wanted a pointer to an integer, we would create a pointer and then do a write to it. I guess in C you can do the same thing, except you have to put in a cast. And sort of the difference is here, this kind of update is safe. Yes? So the question was, when you do a write, do you lose the ability to read? And the answer is no. And you see this in both read and write. You give read and write a capability. And what they'll do is they'll give you back a capability. So if you've written in a functional program, if you want to implement the state monad, you do this in a kind of state passing style. And the same thing happens with linear types, except we're passing capabilities around. And with the linearity means that we can implement the state passing style with an actual state. So let us write a little bit of code. Yes?
Is T what used to be G?
No, T is a new type constructor. So let me see if I've got a. So what we're doing is we had all our old types, including F and G, and we are adding the type pointer of X to the intuitionistic side, and to the linear side, we're adding a capability type, saying I have ownership of this location in memory, and then I'm adding a new type T, which represents imperative computations. Yes. Yes. So this is something that will actually get simpler once we have dependent types, which is not a claim that can often be made. But what's going on is that the type pointer of X is you can think of X as the address, and pointer of X as this is the type containing that single address. And so the reason we put this into the type is because we've split pointers apart into the address and the particular place in memory. And so when we do something like a read or a write, we need to know that the pointer we pass in and the capability to access that memory are actually the same address. Yes. What? Why do we need t? Let me show you. So we have this foo, right? And when we invoke it, it gives us a pointer. And we can see what address it printed out. Let's run it again. It's not the same address. Let's do it a third time. It's a different address still. So what's going on is that the specification of a memory allocator is generally non-deterministic. And this kind of non-determinism is a side effect. And if we didn't have the monad to deal with the allocation, then the equational theory of the linear lambda calculus would get weaker. So you would only get sort of the call by value equations rather than the full beta eta theory of the linear lambda calculus. Yes.
Oh yes, in your write operation, I know we're supposed to be like coding up the computational interpretation of things, but what justifies changing the type of the format keeping the same pointer?
Okay, so the question was, why is it safe to change the type of whatever we wrote to? Let's mute and up again. So okay, so that's a good question, and this is the reason for it is, in a nutshell, linearity. So in a language like ML or Java, when you get a pointer, you are not the only person who has this pointer, or you might not be the only person who has that pointer. So if we're running a program and you receive, say, a pointer to integers, it's entirely possible that some other module has a reference to this pointer, and it's going to expect that there's an integer there. And so as a result, if you do a write to that pointer, we can only safely put in integers, because otherwise we could break the expectation of other clients of that pointer. But in a linear type system, what happens is that if you have this capability, you know for sure that you're the only owner of this capability. There are no other accessors, and so that means that because you're the only part of the program that has this capability, you can do the update and change its type, and because you're the one who just changed it, you know its new type.
Well, I have a never more complicated concern about it.
Uh-huh.
I know, let's say you do your X was once int, and now you're storing some massive type.
Yeah.
And then ensure to every point that you sort of define space with your pointer, you have to use the pointer.
Uh-huh.
But you encoded and you're right. There are no writings that your pointer can change location.
Right. The invariant is that we haven't changed the location. Okay. Yes. So that's a good question. So the question was basically a question about data representation. If I can reparse what you're saying, so in C, lots of different types have different sizes. So like a char might be 1 byte of memory, and a double might be like 8 bytes of memory, and a pointer might be 16 bytes of memory. And so if we have say a pointer to a char which is only 1 byte of memory, then is it safe to change that to a double, which might be 8 bytes of memory? The short answer is, in general, no. The idea here is that we have like a uniform data representation like ML or Java would, where everything is the same size. And so you could change the type arbitrarily. So if you did want to track that kind of information, you could make the type system a bit fancier to track the size of each type. And then the type of write would be, you can change the type as long as the type has the same size as it did before. Yes?
Is it possible to model pointer and capability in another way so that we can have like pointer to linear type?
Okay, so you want a pointer to linear type. Yes, you can do that. And that's actually what Amal and Matthew and Greg did originally. Instead of having a pointer to an intuitionistic type, they had a pointer to a linear type. So for technical reasons, starting tomorrow, this is more convenient, but you can encode one in the other. Yes? Sorry, I couldn't hear what you said.
Why is the range of the right function sort of using this PPL?
Okay, that's a good question. So the question was, when we did this right, the pointer seemed to go away in the return. And the answer is we don't need to return the pointer back because the pointer is an intuitionistic value. And so we can just keep it around and use it. So we don't need to like sort of thread it through the program. Any more questions? Yes, so in the read, we have our pointer and we don't return it back in the result. And again, it's the same reason that because pointers are intuitionistic, we can pass the pointer to read and we still have it on hand for continued use. Okay, so how is everyone feeling about reading and writing with linear types? Okay, there seem to be a lot of happy people. Let's see if we can fix that. So now I mentioned someone back there. I can't remember who asked why do we have this monad? And I said, oh yes, the reason is because we want to preserve the equational theory of the linear lambda calculus. So let me sort of explain what that means. Let me leave this here, and then I'll. So whenever you have a type theory, like every well-behaved type theory will come with a sort of equational theory associated with it, and the idea is there's a lot of motivations for it, but one motivation which you saw, I guess you saw last week, was the motivation of logical harmony, which says that if you have an introduction followed by an elimination, you can get rid of that. And likewise, an elimination followed by an introduction can also be gotten rid of. So these correspond to what people call the beta and eta reductions. So for each type in your type system, you'll get a pair of equations telling you like when two programs are equal. So for instance, for the unit type, if you know, so if you have E of type unit and E prime of type unit, then we can just say these two terms are equal. So any two terms of unit type are equal. And this is the eta rule for the unit type. So let me write eta here. And because there's no eliminator for the unit type, there isn't a beta rule. And at the product type, we'll have we'll have two equations which say that if we have a pair and we project from it, this is just the same as the first component. And likewise, if we project the second component, that's just equal to the second component. So if we have, we just take the second projection of a pair E1, E2, that's exactly the same as E2. There's no way for a program to distinguish these two programs. And likewise, we also know that at a pair type, if you have a pair, like an arbitrary term of pair type, that's going to be equal to pi 1 of E, pi 2 of E. So this is like beta 1, beta 2, and this is the pi rule for eta rule for pairs. And we can go through and give a similar kind of beta and eta rules for each of the types in the programming language. So probably the most famous one is the beta rule, which says if you have an application that's equal to doing the substitution, and then at function type, so this is x arrow y, we know that every function is equal to its eta expansion, e applied to x. And so, so these equations are sort of justified by the proof theory of your programming language. So you could do like a cut elimination proof or a strong normalization proof or something like that, and then you'll say, okay, yes, we have established the soundness of these equations for the calculus. But if you think about it, just because something is true in the calculus, it doesn't mean that it's necessarily true in an implementation. So for example, if you implement pairs by allocating a block of memory and then like sticking values into each of the components in memory, this program is actually quite different than that one. Because what happens is when you construct a pair E1, E2, we're going to evaluate E1, and then we're going to evaluate E2, and then we're going to build a pair in memory, and then we're going to project out a component, and then we're going to deallocate a pair in memory, and like the entire machine behavior can be very different from just calculating E1. And it's even more dramatic in the case of functions, where if you have an expression, say this is like, I don't know, maybe some big computation, like you're folding over some list of functions to compose them all together, that could take a very long time to do. Whereas like in most implementations, if you write down a lambda term, that's just going to allocate a closure, just like Amal did in the last lecture. And that'll be very quick. So again, the operational behavior of the two sides of this equation can be very different. And so that means that when we do an implementation, we have a proof obligation, which is to show that these equations are actually sound in under the implementation strategy that we've chosen. And the thing that we'll need to do is we'll need to give an operational interpretation to our calculus and then do a proof that each of these equations continues to hold. And to do that, we'll end up using a binary logical relation. So first, what we'll do is I'll tell you what an operational interpretation for this language with read and write might be. And then we can go and look at the model constructions that we'll use to validate these kinds of equations. Okay. So I was telling you, oh yes, new is going to allocate some memory, and read and write will dereference it and write to it, and so on and so forth. And it's all like very intuitive. But before we can do a proof, we have to like, sort of formalize our intuition into something that we can work with mechanically. And so to do that, we need to give an operational semantics that actually talks about memory and reading and writing from locations. So what we've seen so far in most of the other lectures is we've seen a reduction semantics, and people, I guess, have also told you about the abstract machines. And so what we're going to do is we're going to build an abstract machine for manipulating the heap. So what we've got, let's see, what else do I want to do? Oh yes, before I do that, let me round out this programming language with the monadic operations and some typing rules for them. Let's see. Yeah, let's write some typing rules for T and capabilities and those 4 operations there. So let's just do this. Okay. So because the bulk of the operations are all in the linear fragment, I'll just sort of give syntax and typing for these kinds of operations. I don't want to add them as constants of this type to our programming language because it sort of complicates the proof in slightly awkward ways. So we'll put those operations in, but in a slightly different fashion. Okay. So what we've got is, as of yesterday, we had a judgment which had 4 places, and it said if you have intuitionistic hypotheses gamma, some linear hypotheses delta, and then we can check that a term T has the linear type A. And what we're going to do is we're going to add some typing rules for T of A, and then some typing rules for new free read and write. Okay. And let me just get on that. So T of A is a monadic type of computation producing A. And this means that in addition to the basic operations, we also have like a few structural primitives for computations. So one of the primitives of computation is if you're going to compute something to produce a value, then if you have a pure computation of type A, then we can treat it as a computation. So this is like the return in monadic programming in Haskell. So we're saying if we can build an A, then we can treat it as a T of A. And I'm using val because that's the notation Moji used in his original paper. Okay, and the second rule is the sequential composition rule. And it says that if we can compute, if we have a computation of type A, then we can do sequential composition. So this is going to correspond to do from Haskell. So if we have a monadic computation of type T of C, and we have a computation T of A, we can evaluate this T to get the A, and then continue on with the T prime computation. No, sorry, T of C. Next, let's put in the rules for allocation, and I'm going to write this in a slightly funny way. So So the type that I wrote above said that nu was a constant computation, that when you evaluated it, it gave you a pair of a pointer and a capability. And it turns out that when you're doing proof theory, it's sort of awkward to put in constants at random types, because that will, yes?
So are you now introducing new syntax and the type rule at the same time?
Yes, that's what I'm doing. So I'm giving you, so if you look in the notes that I posted to Piazza, like I've added the new syntax and the new typing rules for them. And the syntax that I'm writing now is the syntax that I'm using for these operations. So for sort of intuition, it's often convenient to say, here are some constants I'm adding to the language. Yes?
Can you write the rest of the rules a bit larger?
Yes, I can do that. Do you want it that big, or?
I can read the left half, but
Okay.
that last one was under big
Okay, let me just rewrite it, and I'll make it bigger. Okay, so we're going to have, okay, let me just do it over here. So, is that better? Okay. Okay, so what I wrote up there introduced some constants, and it said, I'll give you a pointer of type X and the capability. And adding constants at random type will, in general, break a normalization proof. So for the syntactic theory of your language, it's often a good idea to arrange your language so that once you have the introduction and the elimination pairs for a type, there are no other rules which mention that type. So what we're going to do now is we're going to give some rules for this monadic type that don't mention any of the other connectives except for a pointer. Pointer of I. And delta tells me one. So what this is saying is it's saying, here's this computation T, which is a sort of a continuation in which I want a new pointer. And so what's going on is it's saying, I'll bind the newly allocated pointer to X and the capability that's just been allocated to A. And so in the typing of T, we add X, which is a pointer to this, to our intuitionistic context, and we add A, which is a capability, to our linear context. And sort of the trick is that, like, now that tensor product doesn't occur in the rule at all, and so that way it won't interfere with any of the normalization properties for any of the normalization theorem for tensors. Next, let's do free, and for free we're going to do just the same trick. So we're going to say, is this big enough? Okay. Where'd my eraser go? And so what we're going to do is we're going to say we want E to be a pointer. And we want to know that T is something that will give us a capability to access that memory. And then once you can think of it as delta contains the capability to access this memory, and then in our continuation T prime we don't use it. We don't see that capability anymore. Okay. Yes. Okay, so I lied slightly. So if you look at the notes, I was going to get to this, but now is as good a time as any. So in the types up there, I wrote like for all x and exists x, and I talked about like these x's as names for locations. And since we've added these x's to the type, we'll also need a context to keep track of their names. And what I'll do is I'll annotate this judgment with a sigma. And sigma is just a list of names. So what we're going to do is we're going to say that when we do an allocation, we're going to make up a new name for this pointer that we've allocated, and the for all and exists rule for locations will follow the same pattern as for all and exists for the polymorphic lambda calculus. So we are introducing a new context to handle the for all and exists. Yes. Oh, it should be sigma. Yeah, so once we make this dependent, we can throw it into gamma. And so that's the sense in which linear dependent types make this simpler. But today we don't have dependent types. What? Okay. So now let's see. We've done allocation and deallocation. So what time would we have? Okay, less time than I thought. Well, let's go through the typing rules for reading and writing, and then I'll start to sketch the model construction. Okay. So now what we want to do is we want to be able to read and write from a pointer. So what we want to do is we want to say and do I have enough room? Yeah, probably. Okay, and so just like with the other rules, we're turning things slightly inside out in order to like eliminate the number of connectives we're talking about. Okay, and so when we're dereferencing a pointer, we can see up there that we need the pointer and we need a capability. So what we want is we want E to be a pointer, and we want T to be a capability. And once we do the dereference, we'll get access to that value of type X, and we'll get the capability back. So what we'll do is we'll say, we'll put X into our context, into our intuitionistic context, because we've dereferenced this pointer. And then we will add the capability back, and then we'll check that, sorry, that's a little small. And then we'll get back the, this continuation t prime, which will use the newly read value again. And finally, we can do the write. So what we want to do is we want to say, let me give a little more room. A equals, E gets assigned E prime. Okay. So now, in order to do an assignment, we need to know we have a pointer and we have a capability. So we need to know that we have a pointer, and we need to know that we have a capability to access that pointer. And we also need a value e prime to write into that pointer. So we need to say, okay, we want e prime to have some type y. And then once we've done all that, we'll get back a new capability telling us that the pointer now holds a y rather than an x. So what we'll do is we'll say gamma, delta, and A tells us that the location I holds a y. And, you know, what's I guess, standing back here, it looks like sort of a bit more typing rule than I expected. But, you know, once you have this, it's actually pretty nice because you can write a lot of these imperative algorithms in a very functional style. So we'll write down operations to mash pointers around, like reverse linked lists in place and things like that. And that works out pretty nicely. The question though is, you know, how do we run programs? Like, what does it mean? We've given the statics, but now we need like some kind of dynamics for this language. Okay, and so what I will do is I will not just give you one dynamics for this language, I'll give you three. So part of it will be pretty straightforward. So we have a functional language, which is the intuitionistic language of E's. We have a pure linear calculus, which are the T's. And then we have these imperative computations, which are all the terms of this type T of A. So what we'll do is let's say what values are, and then we'll carry on. So what are values? So since we're going to be talking about an operational semantics, we need to pick an evaluation order. So let's pick call by value. And so what we'll do is we'll say values can be unit, they can be pairs of values, they can be functions. And so this is unit, pair, implication. Oh yes, we'll need our G's. So we'll say G of T is a value. So this is a suspended linear computation. And let's see. We also need values of pointer type. Let's see. So I'll write L for values of pointer type. So L are just going to be, you know, addresses. You can imagine that L stands for a 16-byte string telling you the address in memory. So it's a location. And let's see, what else? And that's it. So then let's have a type of linear values. So we'll say, again, we'll have units and pairs, only this time they're the linear unit type and the linear tensor type. We'll say functions are also values, and an f of v will be considered a value. And let's see, now we need to add some add a type of values for capabilities. So the thing here is that capabilities are, in some sense, a purely logical notion. They're sort of saying, you have the right to access this piece of memory. And there's really not any computational data associated with them. So what we're going to do is we'll say, okay, well, we'll represent capabilities by just an asterisk to indicate that here is a piece of data with no computational content. And then once we have capabilities, we need to have values for the monadic type as well. And then I think that will be everything. Well, it's not actually everything, because I really do need to give you values for all and exists type. But I think I'm going to skip that because it's the same as in system F, and I don't have time, and it will go away tomorrow. So what we'll do is, what I want to do is I want to say, I want to differentiate pure linear computation from sort of effectful linear computation. And what I'm going to do is, it's sort of the same trick as in Haskell. A monadic term is just a value in Haskell semantics, and it's not until you pass it to the runtime system that an I/O thing actually does any computation. So what we're going to do is we're going to say all of these monadic terms are actually values. So val of u is a value, or let's even make it val of t. Yeah, why not? Free. T prime. Read. And okay, so we're treating all of these computation terms as values. And the first two reduction relations we're going to give are a pure reduction for intuitionistic terms, which says E steps to E prime, and a pure reduction for linear terms, which says T steps to T prime. And both of these are going to look exactly as you expect. So let me turn on the projector again. And let's see, how much time do I have? It looks like about 5 minutes, actually. So why is there no signal? There we go. So we have an operational semantics here, and you can see that we have the steps to relation, which has all of the beta reductions you expect. So up here we can see that functions get applied by substituting. The first and second projections work by giving you the first or second component of a pair respectively. And then I'm just writing all the congruence rules by saying I is a frame. I'm just going to skip over all the congruence rules because they're numerous and boring. And then the same thing happens in the linear calculus as well. So if we have a linear function application, it's the same reduction behavior. What we're going to do is we resolve this by substitution. And then these pattern matching eliminations work more or less exactly like ML or Haskell pattern matching. So when we see let unit equals unit, then we can just drop it because no variables are bound. So let unit equals unit in t, we'll step to t. And if we have a pair, what we'll do is if we say let AB equals u comma u prime, then we'll step to t, but we'll substitute u for a and u prime for b. So it's like we're deconstructing the pair and substituting the two components. And now if we're running a suspended computation, so remember run is the elimination for the G type, then run of G of t will just step to t. And likewise, if we have the elimination for the F type, where we say let f of x is equal to f of v, then what we can do is we can just substitute v for x in t. And then there's like two sets of congruences, depending on whether the evaluation position is a linear computation or an intuitionistic one. And that leaves us with the reduction rules for the computations. And what's happening now is we have a step relation not on terms but on machine configurations. And so what a machine configuration is, it's a pair of a store, which I write sigma, and a term t. And what a store is that it's a list or a finite function mapping locations to values. So here I'm saying, give me a list of pairs of locations and values. And there's the invariant on this that all the locations have to be disjoint. So you can think of it as, here's the domain of the heap, like all the addresses that have been allocated, and what value is stored at each of those locations. And the reduction rules for computations work on a principle of whenever we see an imperative action, we're going to update the heap. So like the most basic one is when we have a val of u. And since that's a computation, a side effect free computation, we're treating as an effectful computation, the store isn't changed. So whenever we see let val of a equals val of u in t, then we can just do the substitution. We can substitute u for t and leave the store sigma unchanged. Let me see if I can make this just a bit bigger. Uh, 250. Does that work? No. Oh well. I think I made it worse. Oh well. Okay. And then in the second line, where this is the rule for allocation. And what this is saying, I have the slightly different syntax in my notes, is that when we call new, we're going to change the machine configuration. So we're going to choose a new location L that's not in the domain of the heap. So non-deterministically, we're choosing a location. So if you remember what that C program did, every time we ran it, Malik would pick a different address to hand to you. And what we'll do is at that location L, we'll stick in a unit value. And what we'll do is in the continuation computation, we'll bind the location L to X, and we'll just pass in this asterisk for the capability. So capabilities are never actually computed with. They're just sort of there for bookkeeping purposes to tell us that I have the right to perform this operation. And one thing you should notice is that in the typing rules I gave you, there are no typing rules for either L's or stars. So there's no way to get like a bare location value or a bare capability. Those are things that are only created by programs while they execute. And like, yes?
If there's no the static preservation is not true.
Yes, that is correct. So this is the type system I've shown you is a type system for programs that the user wrote. So the programs that a user writes cannot have like sort of literal addresses in them. And so what we'll prove along the way to proving the equational theory is a sort of semantic type safety property, which will say that every well-typed program will terminate and return a value of the appropriate type. But we will not have like a sort of standard syntactic type safety property. So that's only possible if we're willing to type all of the intermediate states of the program, and I don't want to do that because I don't want to say that the programming language includes bare pointers in the syntax. Okay. So to repeat, when we allocate a new pointer, we're extending the store here. So this notation with the square brackets you can think of as here is a store sigma, and I'm extending that finite function with a new location. And free is actually going to do exactly the opposite. Did you have a question? Okay. And it says to free a location L, what we need is the location L has to be in the heap, and then when we perform the step, that location goes away. It's not in the heap anymore. And something similar happens with the dereference rule. So when we read from a location, what we're going to do is we're going to say, okay, here's this variable x. We're going to bind the contents of this location, which are v, to this variable x, and then we'll perform a substitution. So the heap doesn't change when you do a read, but we do bind the contents of that location to a variable. And when we perform a write, what we need is for that location to be allocated, but we don't care what's in the heap. So we'll say we're performing L gets assigned to V, and whatever was in L, I just wrote a dash to indicate we don't care about it. We'll replace it with the V and then continue with the computation. And then there are an enormous number of congruence rules, which I will skip over. And so now you understand sort of how the operational behavior of this language works. And so the goal of this, the goal of, do I think I can? Yeah, I'll need to stop soon, but I will close up with just a brief description of how we'll actually establish type safety. And the answer is that we're going to do this by proving the fundamental theorem of logical relations. So what we're going to do is we're going to give a binary logical relation that relates these untyped programs to each other, one for each type. And then the fundamental lemma will basically say every well-typed program is in this relation, and by construction, the relation will be set up that everything in the relation is safe and also respects the equations. So let me briefly describe that. What did he say? I don't have time to go into it in detail. It is going to look an awful lot like what Amal was talking about. So what we're going to do is we're going to have one relation for all of the intuitionistic types, and it's going to be that, for instance, for pairs, that two values are in the pair relation if their first components are related at x, and their second projections are related at y. And functions are in our logical relation if for every pair of related arguments, you get related results. And one of the things that you can prove, I don't know if we'll actually go through the proof, is that this defines what's called a partial equivalence relation. So we had this untyped syntax and untyped operational semantics, and what our relation is doing is it's sort of carving out the well-behaved fragment of that. And we're going to show that every typed program lives in this well-behaved fragment. And then once we have the intuitionistic types, then mutually recursively, you can see we'll also interpret the linear types as well. And the main difference is that instead of relating terms, we'll now be relating machine configurations. And so what we're going to say is that here, let's look at functions, for example. We're saying that two machine configurations are related at function type if given two configurations that are related at the argument type, you can glue them all together and get something related at the result type. And this kind of gluing together bits of the heap is sort of the essence of ownership transfer. So we talked about how having a linear capability meant that you had the right to access a part of the heap. And what we're doing with our logical relation is we're making that very literal. The meaning of a type is a value together with the region of the heap that it owns. And indeed, the type of capabilities, and I will stop with this, are that a capability is just a dummy value, but it tells us exactly what chunk of the heap it owns. It's, yeah, this should be L colon V prime, comma star. And we're saying if the location is X and the arguments are related at X, then that's the interpretation of a capability type. It's basically just the knowledge that you have the right to access a particular piece of the heap. And then finally, we'll be able to tomorrow talk about how this cooks out in terms of being able to perform computation safely. So I'll carry on tomorrow.